Okay, welcome to the third and last part of this series of lectures about the fundamentals of fault diagnosis and fault tolerance. And indeed, today we are presenting these two parts, the fault diagnosis and fault tolerance part. So previously we introduced overall the course and we introduced faults, how they can affect the system, and we introduced the good properties like reliability and availability that a system should have. Now let us look at the part that we control systems engineers would like to design. So we are first of all presenting a taxonomy of different kind of fault diagnosis, FD approaches, followed by a taxonomy of different fault-tolerant FT approaches. So let us start with the first ones, fault diagnosis. So fault diagnosis by itself is not so different than medical diagnosis. So surely we took inspiration from medical doctors. So we have some famous doctor here, and we have a patient, and we can draw parallels to what we are doing. So the patient is our system. We want the patient to behave in a nominal way, to be healthy. And then we have the doctor. So this is us, and this is also the fault diagnosis system that we are going to implement. So the doctor has a knowledge base. So they spend a good part of their life learning for a good reason, to fill this knowledge base with what? With what is the nominal behavior of humans, the patients, and in particular, what are normal variations in this behavior, because not everybody is the same. So my body is different than your body. Okay, most of the things are working the same, but maybe my blood pressure is not the same as yours, but still we are healthy. So there is physiological uncertainty. So by physiological uncertainty, we refers to variations that are anyway still acceptable. Then the next big part of the knowledge of a medical doctor is knowing diseases. So they need to have what we engineers call a class of faulty behaviors. And we assume that this class has n members. So we know about n possible diseases that can occur. And we also know how they are going to show up. So we want to know what are the limits, how the possible range of pathological behaviors. So physiological is variations that are okay. Pathological are variations that are not okay. Once we have all this knowledge, what we need to do, a fundamental thing that a doctor is doing is observing the patient. So asking questions to the patient and doing medical exams or measuring physiological properties like temperature, pressure, saturation of oxygen in your blood, many others. So by taking this observation and combining that with your knowledge, you can extract useful information, not just raw data, but useful information that we call features. So when we look, for instance, at the blood pressure of a patient, you can take the raw number, but you can also say, okay, this is high, this is medium, this is low. So features is a way of reducing the dimension. So from all the possible values of the pressure, you go down to 3, for instance. And once that you extracted your features, you generate what are called symptoms. Take, for instance, the heart rate. Heart rate, let's say, can be low, medium, or high. If I have a high heart rate, so that's a feature, it may not yet be a symptom. Maybe it is not yet an indication that I have a disease. Because if I was running, having a high heart rate is perfectly normal. So symptoms are a further processing of features that take into consideration also all the other information that we have. about a system. And once we do that, we finally evaluate these symptoms and we decide whether there is disease or not. So for instance, if my heart rate is high, but I was not doing any activity, then when I look at this information all together, I might say, okay, you have a high heart rate, you have what is called tachycardia, and that's not good. So you see there is a lot of steps in starting from your system, the observations, and getting to the diagnosis. And all the things that a medical doctor is doing, we can replicate when looking at a technical system. And let us start with the first step, the one of extracting features. So there are several ways that we can extract features from a dynamical system. And the first category is the one that historical was used first. It is also the most simple. It is called signal-based. And the reason for that is that it is based on measuring something over time and evaluating how these signals are varying over time. So the first thing that you can do with a signal is to plot its raw value. Which by itself is not very informative because you didn't do any dimensionality reduction. You just take it as it is. So next step could be, okay, let's look at some properties of the raw signal over a time window. Let's compute the mean value or the standard deviation of that. So there are ways to characterize it with statistical features. Or maybe we look at peak values over a time period. So is the maximum signal that or something else? What is the minimum? But you can also try to do something even more complex. You can do some Fourier analysis, for instance. Or that could be Fourier of wavelets or other things. Or you can compute other more complex things like the Chebyshev. Or you can look at higher statistical moments like, for instance, the kurtosis. There are many, many things that you can do. On the other side, we have another category of approaches that are called model-based. So all the operations that you have there, they don't require you to know anything about the system, any model about the system. They are simple to implement, but of course, there are less knowledge in that. So model-based approaches are more advanced because you are using knowledge that you have in producing features. So one way to produce a feature out of raw measurements using a model is to take the measurements and run them through an observer. So we mentioned that observers were going to be important. So we can look at the estimation error of an observer. Can be also a Kalman filter, of course. This is a feature that's more interesting than the raw value itself. So the raw value of something can take a lot of values, but the estimation error of the observer, whatever you are doing, should be small. And so in this case, it's much, much easier to see when something is not behaving nominally. Let's, for instance, think about the speed of a car. The speed of a car can take a lot of values, can be small, high, can be reverse. So if you just look at that, it's difficult to say whether the car is working properly or not. But let us assume you have a model of the dynamics of the car that takes into consideration how the driver is pushing the pedals, whether there is uphill or downhill, if there is wind or not. So this model can tell you what should be the speed of the car. The observer can be built for reconstructing these and other variables. So normally, the car should be behaving as your model, if your model is good, of course. So even if the car is accelerating, braking, going forward or reverse, still, this is going to be a small number. So that's very easy to see when something is wrong, because then this is going to be a big number. Okay, so other things that you can do is to introduce something called parity space relation. So parity space relation are another way, basically, of expressing a dynamical model. A very simple example could be, in a system, the velocity is the derivative, time derivative of position. So if you take a measurement of the position of an object and a measurement of the velocity, the relation is telling you, okay, derivative of the first should be equal to the second. When the two things are not matching, then something is wrong with the sensors. And that's quite similar to implementing an observer, but there are some subtle variations. For instance, you can already imagine that this approach is leading to much noisier results than this one. Because when you have an observer, you filter out noise. When you directly compute a derivative, like in this approach, you are amplifying noise. So there are several reasons why this one is preferable. Another class of model-based approaches is called model parameters estimate. So what you can do is, instead of building an observer or instead of checking a parity relation, you can estimate parameters. Let us assume you have a very simple example. So a mass spring damper system. So the acceleration, so x double dot, is equal to minus k, elastic constant, that multiplies position of the mass, minus v, that is the friction parameter, multiplying the derivative of the position. So you have this system here with your spring and the mass hanging somewhere. So x is the elongation of the spring. Okay, so what you could do is continuously take measurement of this and then use some algorithm to estimate k and b. So you have some knowledge of what are normal values for k, the elastic constants of the spring, and the friction coefficient b. So if your estimate k, let's call k hat, is different, much different than k, that is k0, let's call it, some nominal value, then you say, okay, I have a faulty spring. And that's interesting to see how, in this case, indeed, extracting a feature is reducing the dimensionality of the data you need to deal with. So in this approach, raw values, you can have a lot of data sampled over time. So you have really high dimension space where to look for faults. But when you do something like that, you end up with two numbers, two scalars in this case. In this case, the dimension is much lower. It is much easier then to detect a fault. Okay, but extracting features was one of the steps. So let's go back. So extracting features from observation is the first step. The next is to generate symptoms. And there are different ways of generating symptoms. In the signal-based case, you need some knowledge of what a normal signal looks like. It is a way to say that you need a model of the signal. So in a hidden way, signal-based modes are some way model-based approaches. But the way to draw a line between these is that a model-based approach is using a complex model, can basically model the entire behavior of the system. A signal-based approach is just using a simple model that can even be static and just models that specific signal. So you don't get extra knowledge. You cannot use that to simulate the entire system. So in the signal-based case, you're looking for something like some normal behavior of your signal. Let us assume that you have a Fourier analysis of something, so maybe a machine, a rotating machine. So if you look over frequency, if this is the nominal rotation speed of some axle in the machine, you expect to have a number of harmonics. And normally, your machine is that you have 3 harmonics. So you have the fundamental, the first, and the second. If you look at your signal, and for some reason you get another harmonic, like this one, this is an indication that something is wrong. So this could be some resonance that you get in your system, maybe because the bearings are failing. Instead, in a model-based approach, you can look for a behavior like this one. Let's go back to the example of the mass spring damper system, and let us look over time. What is the value of the estimate you get, k hat, of the elastic constant? So you have some nominal value that is your k0. Normally, your estimate is some noisy value around here. It's noisy because measurements are noisy, because you have uncertainty, physical process uncertainty, and so on. But after a fault, something like this is happening. So the value you estimate start to be quite different than the nominal one. At this point, you detect a fault, because this distance here is big enough to say, okay, this is no longer physiological, so this was the physiological variation. This is pathological. What we want to do, of course, is to ignore physiological variations. No reason to be alarmed from that. But we want to detect pathological conditions. To do that, we introduce something that are called thresholds. If we go back to this example here, we can introduce a threshold like here, below and above. So we can say that everything that is here is physiological. So the elastic constant k can take any value here, and that's fine for me. But as soon as I get outside of this interval, so this interval is defined actually by a lower threshold and upper threshold. Well, as I am outside, this is pathological. And this is the biggest issues in designing a fault detection algorithm. Because you want this to be large enough such that physiological variations doesn't lead to false alarms, detecting a fault when there is not. But, of course, you want this to be small enough such that as soon as you have some pathological conditions, even small, you want to detect it. Unfortunately, there is no silver bullet here. There is no way to design a threshold that can be optimal both from the point of view of false alarms, which would mean big, and missed alarms, which would make that very small. You need to reach a compromise. If we frame this again in the medical language example, as we said, we ignore physiological changes and we detect pathological ones. And to do that, we take a symptom, we evaluate that, we compute a measure of this symptom, and then we compare it against some known pathological threshold. And this all boils down to solving a change detection problem. We take a symptom, we compute something out of that, and then we compare that to a threshold. This is, in essence, what a change detection algorithm is doing. And this could be as simple as taking the symptom as it is and comparing to a fixed threshold, as we did in this example. We have a symptom as it is, and we compare it to a fixed threshold. But you can do more complex things. You can have thresholds that are time varying. So there could be situations maybe where you want this to be wider for some reason. And if you do like that, for instance, as I'm doing now, this is bad because I'm hiding the fault in this case. Let's move forward in formalizing this a little bit more. So once we have all these machinery in place for extracting features, turning them into symptoms and evaluating symptoms, then we use these to answer a number of questions. We already anticipated that. So the first question is the one related to detecting a fault. And the question is, does the null hypothesis stand or not? And the null hypothesis is the system behaving in a nominal way? This is the null hypothesis. So I know what is nominal, and I ask myself, is the system behaving in a nominal way? Normally, you answer yes, yes, yes. At some point, you answer no. You have a fault then. When you have a fault, if you remember the sequence of steps, we need to isolate that in order to be able to know which fault is present. In a medical case, we want to know which disease is present. So we now need to test another kind of question, and we actually have n of these questions. So the n faulty hypothesis. So if you remember, the doctor has in its knowledge base knowledge about n different diseases. So in the isolation step, we are asking, so okay, the system is not nominal, but in which way it is not nominal? So is the system behaving as if the fault number I is present? So does the patient show the symptoms of a given disease or not? So you ask yourself this question n times for as many faults you have knowledge of. And when you are finally able to answer no to every one of these questions, but one, you got it. You isolated your fault. Basically, it's like saying, healthy, you keep a checklist. O, fault 1, fault 2, and so on, fault n. Ideally, what you would like to do for a successful diagnosis is to check out this. So there is not healthy. Then you want to check out this. And then you want to check out number 3, 4, 5, and everything until fault n, for instance. And you end up only with fault true. At this point, you have an answer, because you were able to prove that the system is faulty, because it is not healthy, and you were able to prove that the symptoms you have are compatible with fault true being present, because they are not compatible with any other fault that you have in your fault class. So if you remember the TV series from where I took that picture with the medical doctor, what they were doing is take the symptoms of the patient and running what they call a differential diagnosis. And it is basically this one. So you compare every possible explanation against every else, and you try to strike out all possible faults, all possible diseases, but one. The only one surviving is your answer. When finally you have that, the final thing is, at least for a technical system, to evaluate how big is the fault. So you know it is that kind of fault, but you want to know how big is that and where it is. For instance, if you have a car and you have a flat tire, you want to know which tire is flat. And maybe also you want to know if the puncture is small or big, because if it is small, maybe you can just run flat and continue until you get to a workshop. Actually, this is how it works in the ideal situation, but sometimes this can happen. You have evidence also against fault number 2 in this example. So that's bad, because you have struck out all the possible explanations for the behavior of the system. So this can happen, and this means that your system is experiencing an unknown fault, something that was not in your knowledge case. It's like a doctor discovering a new disease, which is rare, but can happen. And so when it happens, you need to analyze this faulty behavior and try to add that to your knowledge base. But assume that everything was nice, so you detected, isolated, and estimated your fault. The next thing to do is, well, don't panic, keep calm. You have a fixed time of window to do something before failure. You need to accommodate your fault, which means that you need something in order to reconfigure your system, or physically, as in the examples that we have shown in previous lectures, or to configure that only virtually, to configure the control system in a different way. We already introduced some way these approaches, but let us look at them once more. So in order to implement a fault-tolerant solution, one of the approaches that we have shown is to have that built in your system by design. So that would entail, if we assume a sensor fault only, for example, that you don't use some cheap, fragile sensor, but instead you use a better one that is not going to fail. Let's say a fault-proof sensor. But of course, this is quite a weak solution. If there was such a thing, why not using it from the beginning? And even if there is, it is probably going to cost a lot of money, so we don't want that. So the other approach we have seen is to have backups. So you have your system, you have your sensor, that is failing, and what what you do is that online, as you detect that this happened, you switch to a backup sensor. So here you have some way of switching between one or the other. And finally, the last approach, which basically is the one based on an analytical redundancy, is to take your system that has a sensor that is failing, and you try to compensate that by adding in parallel some model-based approach for fault detection and fault tolerance that is able to compensate for what is happening. So for instance, in this case can work very well when your sensor is not completely failing, but it is showing some drift over time, some offset. So if you have an approach that can detect this offset, estimate the offset, and then add it here back with a negative sign in front of that, then you can cancel out the offset. And this way you can cancel out also other kind of distortions that are happening on the sensor. And so this approach, as I wrote it here, is called adaptive because this is learning over time what is this kind of bias or other distortion that are occurring to your sensor. And indeed, this is more complex from a design point of view because you need a model. You need to be able to estimate things, while these ones are less complex. This one requires still detecting something, but then you just need to have backup sensors. Okay, so we can look at this also from another point of view, from the behavioral point of view that we introduced in the previous lecture. So we said that your system that we described this way as something that has an input U and is producing a measurement Y. Well, this system can be described as a set of possible behaviors. So we take all the possible pairs of U and Y. Then we identify a first set. So this set that I'm highlighting here, B0, is the set of behavior that your system is showing normally, so without a control applied, so open loop behavior. When we add a controller, we have a new set of behaviors that in general can be this one, but applied to the very specific system we have, it reduces it to this intersection here. So the intersection between what your system can do and what the control system can drive your system to. So if everything is okay, this intersection is inside yet another set that is representing your specifications about the behavior of your system. So if it is a car, you want to drive on the road, not off-road. So this can be encoded as a set defining the road that should contain your car, for instance. But the issue is that when you have a fault, the fault is affecting the behavior of your system. So now your system in open loop is going to behave like that. So there is a new set defining the behaviors under the fault. And when you intersect these with the controller, the nominal controller for the healthy system, you get all these possible behaviors. This is not good because they are no longer contained in the specification set. So there are some behaviors here under a fault that no longer match specifications. So this is bad. So the idea of reconfiguring the control system in order to accommodate the fault is to change the controller as well. So we introduce a new controller that now has this set of possible behaviors that intersected with the faulty behaviors we have now is giving you this. And this is good because now it is contained in the specification set. One thing that you can notice is that on purpose here, this new set is smaller than the one that you had here. It means that during a fault, usually, you have much more constraints, and so the behaviors that you can express are more limited. But in this case, still, we were able to stay inside the specification. So this is what we have shown at the beginning as new operating conditions that even in the presence of the faults that are safe and satisfying because they are inside the specification set. Of course, not always this is possible. Sometimes it is not. And then the only solution is you need to stop the system. So you need to have at some point what is called a fail-safe mechanism. When there is nothing you can do, you stop in a safe way. Okay, I hope that at least from an intuitive point of view, this makes sense. And that was also the end of today's lecture. So what we introduced is an overview of fault diagnosis based also on a parallel with the problem of diagnosing medical conditions, and an overview of fault tolerance approaches. So we introduced some taxonomy and some definitions. So not tomorrow, but next week, during the next set of slides, we are going to talk about the system structure, so some structural analysis and some models to define how components interact together. And this is called the components and services model. Thank you.